So, welcome students to the fourth lecture of biomolecular spectroscopy. We are discussing theory of absorption of light by atom or molecule and how propagation of electromagnetic wave happens through space. So, till now we have seen that there are discrete energy levels for any molecular or atomic spectra, and there is definite energy gap between these electronic states, and when our EM wave like a energy matches with the energy gap between these states, then transition happens, right. So, and to explain that, we had come up with a theoretical concept of Jablonski diagram. What we have seen that there are different or discrete energy level S0, S1, S2, S3, and when we shine a light, when the energy between S0, S1 or S0, S2 or S0, S3 matches with this energy gap, that means delta E matches with H mu, then absorption happens. So, the ground state origin, the absorption transition usually originates from molecule lowest energy electronic state, that is ground state, as the most electron reside there under the normal temperature. So, what we are saying, if there is no thermal fluctuation, most of the energy or most of the say particles are here in the ground state in case of electronic spectra. Just to remind you, that is not the case when we are looking at the NMR spectroscopy, because their energy gap is very small, right. Here most of the particles are in the ground state and few particles are also in excited state, that is governed by Boltzmann distribution, right. So, now the absorption transition usually originates from the molecule lowest energy state, which is this one, right, and then in normal temperature this is the case, and then when we are shining and light, say this is my light coming here, shining here, and that is matching with this delta E. Now, what will happen? The particle from here that will go to the excited state, that is what transition happens. So, we can have an analogy, the energy absorbed must be precise amount to match the difference between electronic state, like you know, we were discussing about this elevator, right. So, or when you are climbing a stairs. So, if you put your foot up of this much only, then you go to the next step, otherwise if you are somewhere in between, you will fall down, you will not go. So, that your effort to put your foot up should be equal to the height of those stairs, right. Now, when the particle has gone already, what happens, right? They are now in excited state. So, you know, nobody wants to be in excited state, they have to cool down, they want to come back. Now, they can come back by doing something. Easy way to come back, dissipate the energy, right. Suppose when you are in excited state, what you should do? There are two ways you can calm down. One, sit quietly and meditate, right, your energy will be dissipated, that is, you can call it non-radiative process. And the other way, you do something like you basically to dissipate energy, you do some action. I do not know what kind of action, but some action if you are doing, those are you are dissipating energy in some action, that will be called radiative process. When energy is lost through non-radiative process, we can call it vibrational relaxation. This happens very rapidly, there is no light emitted in this process, and the particle from excited electronic state comes to the ground state, like if you look at here, this is coming down. So, different vibrational state, and this will be called as we can call it internal absorption or vibrational relaxation. So, what is the mechanism? The absorbed photon energy is dissipated as a kinetic energy to other vibrational mode within the same molecule or even to the surrounding molecule. That is what energy is dissipated, right. This was energy dissipated. So, to take this molecule, so take the particle from the ground state to excited state, you shine a light, that is called absorption. And when they when they come from different like electronic state to the like S3 to the S2, that will call electronic internal conversion, and finally by some non-radiative process if it comes down, that is called vibrational relaxation. So, it is a very rapid non-radiative process where excited state electron transition between different vibrational state within the same electronic state. If you look at here, within the same electronic state this energy is getting dissipated, and here from different electronic state this is coming here, that is internal conversion, this is called vibrational relaxation. In both of these cases there is no radiation coming out, radiation was only used here for exciting from ground state to the excited state, these are non-radiative process, right. So, that is the first pit stop, vibrational relaxation. So, internal conversion it is also very fast, it is a non-radiative that moves an electron from an vibrational level to one of the electronic state to a different vibrational level in a lower electronic state, as we saw here, from one electronic state a different vibrational level here to another electronic state different vibrational level here, that is called internal conversion, right. But you remember one thing here, what we are seeing, if electron has gone like up, they will come back as above. So, spin multiplicity is not happening. If it is going from ground state to excited state like down, they will come like down. So, no spin multiplicity is happening here. The mechanism it will happen occurs due to overlap of vibrational and electronic state, which is most probable at the higher energy state. If you look at here, the gap is diminishing, and that is how easily they can come up. And there is a competition at S1, while it is very fast internal conversion, the first excited state to the S0 state is slower because of larger gap. So, from here to here coming can be very fast, but if he has to come from S1 to S0, that will be slower because the energy gap is larger, right. But all the time they will not come like this, all the time they cannot follow the non-radiative process, sometimes they follow the radiative process, and that is giving very important spectroscopy phenomena that we call it fluorescence, it is a radiative decay. So, what happens here, say now by doing all sorts of internal conversion, they have come to the first electronically excited state. From there, if they radiate energy and come back to the ground state or different vibrational level of the ground state, that is called an fluorescence. So, an excited electron relaxes from the first excited singlet state to the vibrational level of ground singlet state by emitting a photon. This is allowed, and it is a radiative transition. That means the spin multiplicity again not changing, it has gone like this, it will come like this, if it has gone like this, it will come like this, spin multiplicity remains same. What I mean, so suppose these two electrons were like this, and this electron moved to here and then like this, it had come to here like this, and then when it is coming it is still like this. So, if you look at finally they are eventually like this, that means 2s plus 1 is 0 because both of these is 0. So, spin multiplicity is not changed. You can represent basically a straight downward arrow in the Jablonski diagram, which is given in this color. That is the fluorescence that is happening. So, to sum up what we have discussed till now, absorption going up, internal conversion by non-radiative process coming here or here, right, a vibronic relaxation, and finally one radiative process that is coming from S1 to S0, that is called fluorescence. So, what is the time scale that happens? Fluorescence is a radiative decay. This happens very fast, 10 to the power minus 15, but this happens because now electron is coming and taking over some stoppage. So, this happens relatively slow compared to absorption, but still it is quite fast, 10 to the power minus 9, that is nanosecond to microsecond or sub microsecond times, like a microsecond time scale 0.1 microsecond or so, that is the time scale that we have. Now, wavelength, if you remember, this guy has lost the energy while coming here. So, the wavelength of this or energy of this will be compared to less with respect to absorption. So, absorption you require more energy, emission you basically emit less energy, therefore, wavelength will be longer, emission wavelength will be longer. So, emitted photon has a lower energy, therefore, longer wavelength than the absorbed proton, right, and the energy is getting lost in vibrational relaxation or internal conversion, and if it is shifting towards the higher wavelength, it is called Stokes shift. Now, one concept that we are going to also discuss in the next class called spectral broadening, due to variety of vibrational levels involved here. It is not just happening like we saw in the atomic absorption, it is possibly that it is not coming only from here, it can come here, here, here and here, and all of them give one line, one line, one line, one line, and this is not a single transition, but a spectrum of the transition, that is how it is brought typically. So, rather than a single sharp line, you have a broad spectrum. So, the dominant path for coming from S1 fluorescence is the most common radiative path from the lower vibrational level of first excited state, because of the faster non-radiative process like internal conversion, it already occurs at the different energy level, and therefore, you get a spectrum rather than a sharp line, right. So, that is the fluorescence. Now, it is also possible that the spin flips, nobody has asked it to come, it went like this, come like this, right, or went like down, you come like down. It can transition from up state to down state. Now, what is happening here? Two electrons were like this in the ground state, it went like this, but somewhere in between it changed its mood and became up. Now, one electron was up here and another became up here. So, both are now up, that means spin multiplicity is going to be 3, and that is what it is called triplet state. But you see, spin flipping is not a faster step, it takes time. So, spin flipping, that process from down to up takes time, and therefore, it is a slower process. So, when it comes from here to here, it takes time. So, this process of spin flipping is called inter-system crossing. From down state it goes to up state, and this is also a non-radiative process. Excited electronic charge of a spin multiplicity transition from an excited singlet state to an triplet state, and this requires the flip flop of the spin, that you can represent as a horizontal curve line. Now, in the triplet excited vibrational state, from here again non-radiative process come to the V0 of T1, and from there it comes back to the ground state, So, you see it took so much time, now this radiation is coming, this is again a radiative process, and we call this as a phosphorescence. So, fluorescence was coming straight from here, phosphorescence was triplet to again S0 state, it takes time, therefore, phosphorescence is slower compared to the fluorescence. Phosphorescence is slower compared to the fluorescence. Right. So, that is what, because this transition flipping is forbidden, but it happens. Forbidden transition based on selection rule. So, it is significantly slower than the fluorescence, it occurs in the order of the millisecond or maybe microsecond. However, it competes with the fluorescence, right. Fluorescence was coming from here to here, but in case of this intersystem crossing, it is just flipping to the triplet state, and from there a radiative process is happening. So, this we can call it delayed fluorescence or phosphorescence. It is a radiative process from triplet state to the singlet state. Delayed fluorescence, what will happen? Nobody has again asked it to go back here. So, if it goes back here and comes here, then it will be called delayed fluorescence. So, what radiative process we are seeing? Absorption going from ground state to up state, then again from the singlet state it is coming back is a fluorescence, and it crosses the system, it will call intersystem crossing from singlet to triplet. Again it comes by relaxing back to the V0 state of T1. Here it is a radiative process that is coming to ground state. This will be called phosphorescence. It can again go back by spin flipping, but that takes time, and again it comes from here to here, it will be called delayed fluorescence. Right. So, these all phenomena that we see it, absorption happening very fast time scale, femtosecond, that is a radiative process. In this case, photon is absorbing and going to the excited state. Then it can relax, that is called vibrational relaxation. It is a non-radiative process, happens in picosecond time scale, and energy is lost via vibrational transition. Then internal conversion, that also happens as a non-radiative process, happens from picosecond to nanosecond time scale. In this case, electronic relaxation happens without photon emission. Now, another competitive process is intersystem crossing, that is again a non-radiative process, happens nanosecond to microsecond time scale. Now, singlet spin goes to triplet state. Then two radiative process that we have seen, one is fluorescence, that happens basically nanosecond to microsecond time scale, it is a radiative process. Now, emission happens from the excited singlet state to the ground state. The another one which is slower is called phosphorescence. Here is microsecond to several second time scale, that is a radiative. So, this emission is happening from triplet state to the ground state. What are the determining probability of these? So, the time relative time scale of each of the transition directly determines the likelihood, right, what is happening. Faster transition will out compete slower one, right. Faster, that is like a fluorescence, without compete with the slower one. That means, excited molecule is more likely to follow most rapid path to relaxation rather than sitting and waiting to relax. And that visualizing competing pathway, Jablonski diagram provides a visual overview of all possible radiative, that where photon is emitted, and non-radiative, where just dissipated as a heat transition of a molecule. By understanding the speed of this process, the diagram reveals which pathway is the most probable, right, which pathway is the most probable. So, if we compete, or if we see, if you look at vibrational, these are faster compared to fluorescent. That means, probability of non-radiative decay is more probable than a fluorescence. Now, fluorescence is more probable than phosphorescence. Intersystem crossing, here more or less similar to fluorescence. So, it can go to intersystem crossing and fluorescence, right. So, that is what Jablonski diagram gives, and one can control the outcome by knowing the typical time scale, allows to deeper understanding of photochemistry and spectroscopy. Suppose I want to understand a phenomena that is happening in nanosecond to microsecond time scale, I can use this kind of a spectroscopy, because that is probing the reaction or the mechanism or reaction mechanism or any event happening in microsecond to nanosecond time scale. If I want a slower one, we need to choose something which is much slower, like a phosphorescence. If I want to understand the phenomena that is faster, extremely fast, we have to think about absorption. So, what kind of radiation can be used and what kind of phenomena to be investigated in a spectroscopy depends upon the time scale. This is very important. So, some of the real time application we see in biology or in life science or medicine, we use fluorescence microscopy or spectroscopy extensively. You can see what is happening in the cell very specifically by doing this microscopy called fluorescence microscopy. In material science, you have seen your now all the TVs or the computer screen that gives you vivid display, they are also showing some spectroscopy phenomena, and also you can tune your cellular cell for molecular absorption, so that you suppress the non-radiative loss and improve the energy conservation. So, basic concept of a spectroscopy you can use in life science, in the OLED technology, or even in photovoltaic cell, and that is the real life application of a spectroscopy that we are studying today. Right. So, summary on revealing the molecular path, the Jablonski diagram bridges the quantum state and a particular molecular photophysics essential for interpreting and designing materials that interact with light. It also helps in understanding the absorption, emission, non-radiative process that enables advancement across the spectroscopy or bioimaging or even optoelectronics. So, this spectroscopy has a vast application in life science, in photophysics as well as in material science. So, thank you very much, and we will continue our discussion on spectroscopy to be more precise on UV visible spectroscopy in the coming class. Thank you.